It's my pleasure to be here, and today I'm going to talk to you about geoengineering, a very controversial topic. I got trained in this problem through work with Paul Crutzen, who invited me to work on a problem with him about 5 years ago, and I haven't. I seem to be getting deeper and deeper into it, and I'm still having fun at it. But it's quite a controversial topic. The work that I do is funded by a small foundation. There's no support for this kind of work through my lab itself. So I've been using it to support postdocs and young scientists working with me. So for those of you who don't know what geoengineering is, it's also referred to as climate engineering, and it's a term used to identify the intentional change in climate system introduced to counter some of the effects of increasing greenhouse gas concentrations. There are a variety of methods for doing geoengineering, and I'll tell you about a couple of them in a few minutes. The reason people are considering it is because of the concerns that society is not adapting or changing its strategies for mitigating climate change rapidly enough, and there may be a need for something more than that. And because of that, people are considering the possibility that perceptions and comfort levels and strategies might change when considering the introduction of climate change deliberately rather than carelessly. And that's introduced a lot of conversations, both among scientists as well as considerations associated with the ethical and moral issues that are around it, and the difficulty of engaging on stuff like this with respect to negotiating treaties as well, the political issues. Okay, so I don't have to spend much time on the energy balance here. For this audience, I know. I'll just tell you that, in essence, the ways that geoengineering are implemented is by interfering or introducing ways of attenuating or modifying the amount of sunlight reaching the surface, increasing the reflectivity of the planet, and having more sunlight be scattered back to space. There are also some proposals around to change the trace gas constituents in the atmosphere that are responsible for modulating the energy flows in the long wave part of the spectrum as well. So both by drawing down greenhouse gases, that's one way. The mechanism is called carbon dioxide removal, as well as there have been suggestions about reducing the opacity of cirrus clouds and allowing them as well to allow more infrared energy to escape to space, or to escape space more easily. There have been a variety of geoengineering approaches that have been suggested, and this cartoon appeared in a very nice report in 2009 from the Royal Society. I see I haven't attributed it, but I'm going to talk to you primarily about the mechanisms for increasing the reflectivity of the planet. These techniques are called solar radiation management, or sunlight reflection methods sometimes. There are two that have received quite a bit of attention. These are the introduction of particles into the stratosphere that can scatter sunlight back to space, and the possibility of changing the albedo of clouds. This is sometimes referred to as marine cloud brightening. That's right. Yeah, this cartoon leaves something to be desired. These are strategies which have been looked at in more detail than any of the other strategies. And the reason is that the initial forays into assessing feasibility and climate consequences indicate that they're perhaps easier to achieve and less costly than many of the other strategies, and perhaps less dangerous. So the reason that these two have been considered is because we see analogs to them in the present day world. And one of them is through the cooling that occurred after the Pinatubo eruption, when measures of global average surface temperature indicated that the planet cooled subsequent to the eruption by about half a degree over a 1-year period. And then as the particles that were produced by the eruption sediment out, the planet gradually returned back to its the temperature, the global average temperature that it achieved, or that it had before the eruption. There's also in the lower panels indications that there were other responses to the climate system. The red lines in the top panel are various model simulations. The black line are the observations. In the lower panels, these are measures of the amount of water vapor in the planet, and we also see an impact by changing the energy budget of the planet in the water vapor as well. Human beings also impact clouds, and a very easy and dramatic example of this are in something called ship tracks, which you see here. This particular picture, I think, was taken off the coast of California, but you see them in a variety of places in the eastern ocean basins. You see these cloud streaks here that are a result of the introduction of pollution particles by ships that are sailing, freighters that are sailing in the ocean. They can change the brightness of the clouds, the reflectivity of the clouds, in a variety of different cloud regimes. If you look there, you'll see that there are both open and closed cellular cloud formations. There's open cellular features here, closed ones up closer to the coastline. And so these kind of emissions of anthropogenic particles change the brightness of the clouds. The effect is relatively well understood. Some simple theory that was introduced by Sean Toomey a few decades ago suggests that if you introduce additional aerosols in the vicinity of clouds, you form more cloud drops. And each of those cloud drops or each of those aerosol particles are competing for the available water vapor there. And so in the presence of more aerosols, each of the cloud drops becomes slightly smaller. And simple physics suggests that more numerous small drops reflect sunlight more easily than larger particles do. 5 minutes? I don't believe it. This is... Did you time it from the beginning of my talk, or are you going... Because we started way behind the schedule. I've showed about 5 slides, right?
Should have kept straight the chair.
Yeah. Okay. So I can't believe it. Natasha, go back to it. Yeah. Okay. So anyway, Tony Slingo did a nice study in the 1990s showing what a strong impact this could have on the radiative budget of the atmosphere. There are impacts that have been noticed after volcanic eruptions in other fields. Kevin Tranberth and Igo Dai did a very nice study where they showed that they could discern a response in the river runoff of the planet as well. So we see some changes from changing the energy flows in the atmosphere to the hydrologic cycle, and this has become better understood over the last decade as well. We've begun to do modeling studies that have explored what would happen if we introduced sun shields, sort of idealized studies of the impact of aerosols or the impact of reducing sunlight reaching the surface. The left panel here is showing you the temperature change for a quadrupling of CO2 from a very comprehensive study, model intercomparison study that is taking place right now and over the last couple of years. And the right panel showing you the temperature change that's a result of reducing the amount of sunlight reaching the surface by a few percent. The sort of 14-degree temperature changes that one sees in the wintertime in the northern hemisphere are reduced to 2 or 3 degrees. The models suggest that there would be also strong impacts on precipitation distributions. The left panel is showing you the changes in precipitation from a quadrupling of CO2, and the signatures that are seen have been well understood or seen in many models over the last few decades, with an increase in the strength of the hydrologic cycle, particularly in the tropics. Introducing the geoengineering reduces the strength of the hydrologic cycle, which is of some concern to the scientists, and of course it would have impacts on society as well. Oops. There are other consequences that have already been explored in modeling groups. Simona Tilmas did a nice study in 2009 in which she looked at the impact of stratospheric aerosols on ozone. It ends up that the stratospheric aerosol particles are sites for surface chemistry that's responsible for ozone depletion. And by increasing the number of aerosols in the lower stratosphere, we would anticipate there would be an impact on ozone by as much as 10% at high latitudes, with an increase actually in the ozone amounts in the tropics. Now, this is a new cartoon for me in which I've tried to describe the impact of geoengineering and its impact on some climate metrics in terms of a bullseye here. And what I want you to do is to focus on the goal of geoengineering being to keep the planet in the center of the target here of what I'm calling a pristine world, a world relatively unaffected by anthropogenic changes, and anticipating that with increasing CO2 or some other greenhouse gases, there would be a push to move the planet into the outer rings with increasing effects on climate. I'm going to introduce a couple of axes here, with the vertical being for more and less precipitation and the horizontal being lower and higher temperatures, and then just say that what we anticipate is that the effect of increasing CO2 is to push the planet to a stronger hydrologic cycle and higher temperatures. The point of geoengineering is to return the planet back to the center of the target, but what we find from modeling studies here is that they don't do a perfect job of this, that they're inexact, and that, in fact, because of the physics that we're perturbing on the planet, that there's not an exact compensation. If one was to return the planet to a temperature which would be very similar to the pristine world, then the rainfall would be different. We can adjust the amplitude of the geoengineering effect, but we're never going to intersect precisely with the center of that circle. And our experience with models up to now is to see that both for these measures of precipitation and temperature, this inexact compensation is true, but there are also other effects, like for sea ice as well, and I won't go into that in any more detail. However, the modeling studies that have been done so far are also suggesting that when one measures the changes in the planet after the introduction of geoengineering compared to the changes in the planet if you were to do no geoengineering and just allow greenhouse gases to continue to increase, geoengineering is generally doing a pretty good job of returning the planet to something that looks more like a present-day world than a high CO2 world. A nice study done by David Keith and his students evaluated this here. In this case, the length of the blue bars are indicating the amplitude of the change in a world with only doubling of CO2, and the length of the red bars is indicating the amplitude of the change when you do geoengineering as well. And in almost every region of the planet, in the context of this model, the geoengineering is returning the planet to something that looks much more like the present day than doing no geoengineering. And this is the case for other metrics and other models as well. Thanks. Now I believe you. So Alan did a very nice study a few years ago in which he explored the consequences of introducing geoengineering for some period of time starting at 2008 or something like that, and the colored lines here are showing the impact on the global average surface temperature of various amounts of geoengineering, and then considered what might happen if, for one reason or another, we needed to turn geoengineering off. And what you'll see, in this case he turned it off in 2030, is that the surface temperature returns to values much like the world in which, with no geoengineering, the red line, very rapidly. Within a couple of decades, the world would have warmed back up to temperatures which are very similar to those that would have occurred if you had not done the geoengineering at all. But what you will notice is that the rate of change of temperature post-2030 is much, much higher than the rate of change of temperature if we had not done geoengineering in the first place. And there are impacts both for human systems as well as for ecosystems in those kind of temperature changes. So that is a risk that we would develop by introducing geoengineering. Now, CO2 lasts a long time in the atmosphere, thousands of years, as we've heard a couple of times earlier on today. And in principle, if we were to allow continued fossil fuel burning and not find some other mechanism for mitigating CO2 concentrations, you would need to keep increasing and ramping up SRM to compensate for CO2 while it's high. But there are other strategies that one might consider using geoengineering, and I think that this is one of my last slides. And what Steve Smith and I did in a recent paper was to explore the consequences of using geoengineering in a kind of a more judicious fashion, where you anticipate or you explore what might happen if we try to cap the global average surface temperature change at 2 degrees for a variety of scenarios. These scenarios are in a variety of different models. In fact, these sets of scenarios are for models with different climate sensitivity and different rates of mitigation. And the point is that one could consider using geoengineering for a relatively short period of time, let's say 40 or 50 years, while mitigation was operating to draw CO2 down, if one was confident that we had a strategy in place for reducing CO2. So the take-home message of this study was just that there is a potential interplay between geoengineering and mitigation strategies. The policy and physical context, the physical properties of the system determine the way we would use SRM, and that shorter periods of geoengineering are possible and might be useful. So, the sticky ideas in terms of John Cook's talk last night, these are the take-home messages for you, that geoengineering ideas are alarming. My personal opinion is we should think them through rather than being an ostrich sticking our head in the sand and avoiding a conversation about them. And my personal feeling also is research in this area is worthwhile. It's pretty obvious from the studies to date that this kind of geoengineering, solar radiation management, is not a complete solution. There are uncertainties of the science, but there are some things that we already know. It's an inexact compensation. There are side effects. I've shown you a few. There are many that we can't or have not yet anticipated and may not be able to anticipate. It's not a complete solution. Solar radiation management doesn't do anything for ocean acidification, for example. There are a different set of risks introduced by solar radiation management. It might make sense to do if there was a clear path to an energy transition and mitigation strategy, and we knew we had made a demonstrated start on it. I don't really think it makes any sense to consider if we can't see a commitment to mitigation, a commitment to changing our energy infrastructure. The risks and benefits are really complicated. Very little attention has been placed on that so far. There would be winners and losers in this kind of a strategy as well, and we would have to figure out a way of negotiating that. And I'll close there and just say, for me, I hope that there's some conversation about this during the question and answer, because there's just all kinds of things ethical, moral, practical, scientific to be talked about here. And I invite your suggestions on ways to move forward.